Hello everyone, I'm Shaohua, a PhD student from BUPT. In this talk, I will show our recently work, One2Multi graph autoencoder for multi-view graph clustering. I will first introduce some research background and the motivation of our work. Then I will present our model and experiments in detail. Finally, I will summarize our work. The first part is the background. Graph clustering aiming to partition a graph into disjoint communities or groups is a fundamental task in graph analysis. Graph clustering have been widely used in practice, such as community detection in social networks and shown in below figures. Most existing graph clustering methods focus on dealing with only one graph. However, the real-world graph data is far more complex. That is, one usually needs to employ multi-view graph rather than single-view graph to better represent the real graph data. Taking the academic network as an example, one graph view can indicate the co-author relationship, while another view can be the co-conference relationship. Moreover, the authors can also be associated with representative keywords and their attributes. Such complex graphs are usually termed as an attributed multi-view graph, which models an interaction system in a complementary and comprehensive way, and has a great potential for more acute graph clustering. Therefore, it raises a problem: how to clustering on such data. Regarding multi-view graph clustering, previous work can be categorized into two types. One type of work lies in graph analysis-based methods, which aims to maximize the mutual agreement across different views. Another stream of work mainly employs graph embedding to learn compact representation of nodes from multi-view graph data. These methods have achieved good performances on many applications. However, such methods discussed before are both recognized and shallow models, which have limited capacity to reveal the deep relation in complex graph data. Graph autoencoder is a typical unsupervised deep learning framework on graph structured data, such as GAE. They are flexible to model deep relations between the nodes and achieve the state-of-the-art results in on single-view graph. The following is a classical graph autoencoder framework. It consists one graph convolution encoder to encode graph with attributed information, and one decoder to reconstruct graph information. This framework motivates us to develop a graph autoencoder for multi-view graph. Next, I will present our method AutoMac in detail. Before we introduce AutoMac, we first analyze the challenges we face in designing the model. First, how to effectively fold multi-view graph information in unsupervised setting. A straightforward folding method is to develop a multi-to-multi model. That is, multiple encoders and decoders are developed, and each encoder and decoder is for each view graph. However, this straightforward method is not effective due to the introduction of noise. More important, The multi-to-multi model only extracts each view representation separately, while the shared representation may be more important for our task. Second, how to make embeddings more suitable for clustering. Node embedding and clustering are usually two independent tasks. So, the end node embedding is not necessarily suitable for node clustering. In order to solve the first challenge, we propose a one-to-multi graph autoencoder. It consists of one informative encoder and multiple view decoder. This structure is more easily to extract shared information and more efficiently. For the second challenge, we employ a self-training clustering objective to utilize highly confident nodes and soft labels to supervise the graph clustering process. Next, we introduce our proposed framework. As we can see in the figure, our model is mainly composed of two components, one-to-multi graph autoencoder and self-training graph clustering. One-to-multi graph autoencoder is composed of one informative graph encoder and a multi-view graph decoder. With a heuristic metric modularity, we select the most informative view and the input of graph encoder, which encodes both graph structure and node content into node representation. Then a multi-view graph decoder is designed to decode the representation for reconstructing all views. Furthermore, we use soft labels generated by the embedding itself to supervise the learning of encoder parameters and cluster centers. The multi-view graph embedding and clustering are optimized in a unified framework, which will make the end embeddings more suitable for clustering. Next, we introduce each part in detail. The first part of one-to-multi is informative graph convolutional encoder. Observing real-world multi-view graph data, we can find that although multi-view information reflects node relationship from different aspects, they should share some common nodes characteristics. Moreover, there usually exists one most informative view dominating clustering performance in many situations. For example, in the academic network, co-author and co-conference relation views both reflect author's research interests, while co-conference view is more informative. We take the most informative graph view A star and node content information X and input to reconstruct all graph views. Here, modularity is used to select the most informative view. The reason for using modularity is that it provides an objective metric to evaluate clustering structure. Then, a two-layer GCN is utilized to extract the shared information. After getting the shared information, we propose a multi-view graph decoder to reconstruct the multi-view graph data. In particular, our decoder is composed of M view-specific decoders predicting whether there is a link between two nodes in view M, where Wm is the view-specific width for view M. Then we sum the reconstruction error of each graph view data and the total reconstruction loss. This model can also be viewed as multitask learning. The multi-view graph decoder provides the multitask supervised signal for the informative graph encoder to extract shared representation, which makes the shared representation more comprehensive and generalized. Next, we introduce the self-training clustering objective. We input our hidden embeddings into self-training clustering objective to minimize the KL diversity between two distributions Q and P. Q is the distribution of the soft labels, and Qij is measured by student T distribution to indicate the similarity between node embedding Zi and the cluster center new J. And the P is the target distribution, and we can see the target distribution P raises Q to the second power to get a denser distribution. By minimizing KL diversity between Q and P, it will make the distribution of Q more dense. Finally, we jointly optimize a one-to-multi graph autoencoder embedding and clustering learning. And we also provide the optimization formulation for each part of parameters in the paper. To evaluate the effectiveness of AutoMac, we conduct extensive experiments. We compare three categories of related baselines and our model without self-training loss, termed as Auto-MA. We conduct experiments on three public attributed multi-view network data and use common used clustering metrics. The graph clustering performance is shown in the table, and we can see the results of AutoMac and Auto-MA significantly outperform the other baselines. In this part, we analyze the various properties of our model. We first validate the necessity of using modularity to select the informative view. One can observe from the table. If we feed the graph view with a higher modularity view into the encoder, our model will achieve better results. It validates that modularity is a feasible solution to select the informative view. Then, to further investigate the effect of multiple views on the learned embeddings for clustering task, we examine the performance of Auto-MA through ending graph view one by one. The results demonstrate that the performance of our method stably increases as we end the view one by one. Therefore, Auto-MA provides a flexible framework to utilize more graph view. Moreover, we visualize the gradients of nodes to validate the underlying assumption of self-training clustering loss. Now, let's summarize the work. We studied the attributed multi-view graph clustering problem. And we propose a novel one-to-multi graph autoencoder method for graph clustering. Besides that, a self-training clustering loss is introduced to supervise the encoder with highly confident nodes. The effectiveness of the method is validated by comparing its experimental results with various state-of-the-art algorithms. If you have any question, please don't hesitate to contact us. Thank you for your attention.